Hi, this is Gordon Parker from Michigan Tech, and in this video we'll use Simulink to model a second-order mass spring damper system. Now I'm assuming you've never used Simulink before, but you know something about representing dynamic systems, in particular state space or transfer functions. Now if you know how to represent systems using either one, you'll be okay, so you don't have to know both. But if you know both, then that's even better. The point is, I'll represent the mass spring damper system both ways to highlight some of the differences. Again, as long as you know one of these representation methods, you'll be absolutely fine. I'll cover setting the integration step size and logging data too. But first, I'll sketch out the mass spring damper system and derive the state space and transfer function representations. I'll even pick an integration step size. Then off to Simulink. Well, let's sketch out this mass spring damper system. So here's a fixed support, here's a mass, and there's a frictionless surface, of course, the magical frictionless surface. Attached the mass to the sidewall with a spring of stiffness K and a damper with coefficient C, and we'll apply this external force F. So if I draw a vertical line from this reference point on the mass, and then stretch the mass out a little bit, like so, from the relaxed spring configuration, that is the unstretched configuration in the top plot, then that will define for us this distance y that we'll use to describe the dynamic equations for this mass spring damper system. And so here we have them, my double dot plus cy dot plus ky equals f. And here are some physical values for the mass, the damping coefficient, and the spring constant in newtons per meter. We'll need those for simulation, of course. And so we can just rearrange the dynamic equation dividing through by mass and plug in these values. And we'll get some nice numbers, of course. So 1 or 0.1 for the damping term, 20 for the stiffness term, and then 10 times f. Now what we're going to do in this example is have the input force be a pulse train. And notice I have it delayed from the vertical axis, the time equals 0 point, by just a little bit. And that'll be one of the parameters that we play around with in the simulation. So this little time delay here is one of the factors that we want to explore how it affects the response. And we're going to set the initial speed of the mass to 0, but we'll have a non-zero initial displacement. We'll just call that y0 here. So again, the purpose of all this, or the motivation I should say, is that we want to explore the effects of the transient response of this system to changes in that delay time of the input pulse train, and also changes to the initial condition in y. So let's look at a couple representations. First, the state space. We'll define a couple states, the first state just being y, so x1 is y, and the second state being the speed of the mass, y dot. So we differentiate x1 and x2 and then represent those time derivative quantities in terms of the states, the x1 and the x2. So the x2 dot gives us y double dot, which we have a dynamic equation for, and we replace the y dot and the y with x2 and x1 respectively. And then we write the whole thing in matrix form, and this is the state equation. So we hog out a little bit of room for the A matrix. It'll be multiplied by x1 and x2, and we hog out a little bit of room for the B matrix, and that'll be multiplied by f. And then by looking at those equations above, we can determine what to put into the different fields of the A and the B matrix. So there's our A, and there's our B. Now we have to do the output matrix. Well, the output, we normally call it Y. Well, that's rather convenient because that's also what we started with on the left side of the image there. So Y is just equal to X1, so we fill in the matrices accordingly, and those are our C and D matrices. So we'll need those for populating the Simulink model in just a minute. So now here's the transfer function representation. Of course, the initial conditions are 0 for a transfer function, so that makes some things easier, but we lose some information when we simulate it, and that's one of the things we'll look at. Okay, so now we take this second order differential equation, take the Laplace transform of it, making that, or exploiting that assumption that the initial conditions are 0, and so we just get s squared times y plus 0.1 sy plus 20 times y equals f. And then just jiggle it around a bit so that we can solve for the output over the input, and in this case that's y over f. So we get 10 over s squared plus 0.1s plus 20. A beautiful little second order transfer function that we can do some further analysis on. Okay, so let me rewrite that on this clean sheet. Here we go. Now, since this is a second order transfer function, the characteristic equation down here can be equated to this sort of canonical form of it, 2 zeta omega ns plus omega n squared, and then we can just extract out the omega n squared term, which is 20, and then take the square root of it to find omega n, the natural frequency of the system in radians per second. So for our case, it's about 4.5 radians per second. And with that, we can go after the integration step size. Now what I'm going to show here is just a really rough cut at it, assuming a fixed time step integration method. And our time step I'll just denote as h in seconds. So here's the rule. Again, very rough. But omega n times h raised to the capital N, where capital N is the integration order for the method that you choose. Now what we're going to do is use a third order method. And so based on knowing that, we can actually get a rough cut of what h should be. Now we do have to pick a value for that much, much less than 1, and I'll just pick 0.01. So we have 4.5 times h cubed, has to be much, much less than 1. And again, I'll just use 0.01. There we go. And now I can take the cubed root of both sides and solve for h. And if you do all that, you'll get about 0.05. You could go smaller than that and you would be okay. Okay, so let's fire up Simulink. There it is. We'll be using that browser of elements to populate our Simulink model. And here's our new model by clicking that funny little icon. And let's give it a name. So Simulink example. There we go. And the first thing we'll do is just, since it was the last thing we did in the previous part of the video, I'll just set the integration step size. So we'll make this a fixed time step solver. We'll choose a third order method. There's only one, so that's easy. And you have to expand this out and then just type in your step size. So 0.05. Okay, so we're done with that. Save it off. Wonderful. Now the first thing we'll do is just kind of work left to right here. So we'll grab the input. Here's a pulse train from the sources field. And I'll just click on here, name it input. Gives it a little bit more meaningful name. And if we double click into this, we can see a whole bunch of nice parameters. So I can set the amplitude. I'll just pick 0.1. Period, I'll pick 20 seconds. This is a duty cycle effectively, so that's 50%. And then a time delay of 1 second. Now, if I go into Properties, I right-click, go into Properties, and then into Block Annotation, I have all these tokens here that describe different features of that block. And by clicking them, and then clicking that little double arrow thing, I can move them over to the right. What this will do is actually provide those tokens to the front face of the model. So it'll tell me what I've actually typed in to that block. And that can be useful when looking at it and trying to figure out what the heck you did if you don't quite remember. And you can add in your own personal annotation in here. So I'll give a little bit more descriptive information like so. You can put in some units. It's actually quite handy. Now normally I wouldn't hard code numbers into these blocks. I would use a .m file, a script file to set them, but for this little introduction to Simulink, it's a good a way as any. And boom, there you go. So now you can see on the front face of the model exactly what you've typed into that block. So it's a great reminder in case you are doing some analysis where you're changing that quite a bit. So now if we go up into continuous, we can grab a state space block and also a transfer function block. So let's populate these, and again we'll just hard code in the values. So here in the state space block, I left click on it and I can just type in the values for A, B, C, and D. Again, I would really never do this normally. I would use a .m file and enter in the values that way so I could manage them better. But here we are. So these are matrices, so you have to type them in with the proper semicolons and so forth. And then we'll put in some initial conditions also, which is a 2x1 array, the first one being the initial position. And I'll put it in centimeters and then divide by 100 because everything is in meters, and put in 0 for the speed. So there's our state space block. Again, I can right click, choose properties, go into block annotation, and I have all these wonderful tokens that I can choose from to populate the front face of the model to show me what it is I actually typed into that block. And hunting around here, we can also get the initial conditions. Aha, there it is. X0, that makes sense. And so now I can give these some more personalized labels. Beautiful. There it is for all the world to see. Now I don't really need to do that for the transfer function block because for this simple transfer function it'll just show it to us on the front face of the model automatically. But here I go, let me type this in. So I have a 10 in the numerator and then the s squared plus 0.1s plus 20 in the denominator. Again, in an array format, so I have the square brackets on each side of these arrays. Now I can take this one input, this pulse train, and feed it into both representations. So now I'm running models of that second order system. Now if I go into the signal routing field, I can grab a mux block, and that allows me to take individual signals, or actually arrays of signals, but condense them down into a pipe. So here I have 2 scalar signals. Actually I'm going to use 3, because what I'm going to do is I'm going to take the input and put it into that mux block also as the first element. But regardless, I have 3 signals going into that mux block, and out the right end of it will come a pipe full of those 3 scalar signals all kind of jammed together. Now let me do some rearranging here to get things lined up nicely. Not a requirement, but visually a little bit more appealing. And oftentimes it'll let you have a more error-free model because you won't have a bunch of lines going willy-nilly. So now I go into the sinks block and grab a scope. And let me change the name of that. Appropriately named inputs and outputs, since it has both things in that pipe. And there we go. Now I'm going to put some labels on here, and this is kind of important because if I have labels on the lines, and I get the labels just by carefully left clicking on the line itself and then typing in a label, if I put those labels there, not only does that remind me of what the heck I've done, but it also will show up in the scope when I turn on the legend. It's a very handy thing to do. Save it. Always save often. And now for logging data. So let's go into this little gear thingy, which we looked at before. But now I'm going to go over here to the data area. And notice this says logs out. I'm going to change the name just so you can see that this name change really has an effect. So I'll just call it crazy data. And that will be the repository of the data that we log. Now I left click on this signal, go into here, click here, so that we log that 3-dimensional array of data. And again, I'll give it a custom name just so that you can see that we have authority to do that. So I'll just call it my data. Save it off. And now you can see this little funny symbol here indicating that we are logging that signal. Change the final time step or final time to 100 and run it. Boom. Runs almost instantaneously. And now let's take a look at our scope. Wow, there's the input. We can see those nice pulses. The blue is the state space response, and the red the transfer function response. Go into this little gear and turn on the legend. And look at that. So now we really know what's what. Inputs, transfer function, state space. Obviously there's a little difference between the red and the blue, and that's because the state space lets us explicitly take care of initial conditions. So we can see this initial condition response. It settles down because of the damping in the system, and then from that point on, the transfer function, the red, and the state space, the blue, pretty much match up identically. So we can really see the effect of that initial condition and the time delay associated with the start of the pulse train. So here's a zoomed view just by clicking on that little magnifying glass thing and drawing a box. And so let me change the final end time of the simulation to something a little bit more representative of what we'll be interested in looking at, and run it again. There it is. Now let me go in here and change a couple things. So I'll just widen out that delay a little bit. And there we go. So we can see a lot more of the transient behavior is apparent, but again it damps out, and then the transfer function, the red, and the state space, the blue responses pretty much lie on top of each other. There, just expanded the final timeout a little bit just so that we can see more of the pulse train in action. This video is really here to help you get started with Simulink, but this is just a little bonus, kind of tooling around a bit with the response results. So let me just set this back. And we could play around with this. If we hit this little button, it will auto size the response. So now with the larger initial condition, we have a larger blue transient, but we can easily fit it onto the plot and look at all of its beauty. Okay, so let's set this back to where we started from. And there we go. And look what I've done here is I've set the start pulse to be about 1.4 seconds, which is kind of a special spot. And you can see what dramatic effect it had on the transient response to the state space. So some things that you might not normally have considered when just doing some hand calculations to figure out how quickly that response would damp out, you can easily explore in this simulation world using Simulink. You can further tune that start of the pulse time from 1.4 seconds, maybe 1.42, etc., and have some other interesting results. But now let's look at the logged data. So if we just type in crazy data at the MATLAB prompt, it shows us a little bit about it, some of the fields. We can see this get element method, and if we now invoke that method just by typing .get method and giving it an argument of my data, because we can see that my data is one of the elements, then we can see more information about what's in there. In particular, what we see is values. So now I'll just issue that same command by using the up arrow and then typing .values, and now we can finally see the good stuff. We have time and data. So now I'm just going to make a couple variables in the workspace. See, I'll call this one time. So I'm just sort of snatching time out of that very strange structure that MATLAB saved all that data into. And I'll grab the outputs. I'll just call that outs. And we snatch that from the data field. And there we have it. And now I can just use the plot command in MATLAB to plot it. And you can see that I pretty much have the same result that I had in Simulink, but using the MATLAB plot command. That gives me a lot of flexibility in terms of configuring the plot into some useful way for a report, etc. Now I can save this structure off, crazy data, and I'll save it to a file called crazydata.mat, and then clear the workspace, and then just load it in. So you can run the simulation, save the data off, close out the simulation, come back 10 days later, and just load in that data. And there you have it. And then using the up arrow keys, I can just re-invoke those two commands to snatch the time and the data out of that structure. And boom, I can make a plot long after my Simulink work is done. Now, just one last thing. I just can't help myself. But you know, this whole example was all about comparing a state space to a transfer function representation. Just showing those time histories on a single plot is a little bit unsatisfying. It'd be much better to show the error between those two things on a single plot, because that's really what we're interested in, is the error between the transfer function and the state space representation. So I just right-click and drag over a mux block, resize it, right-click and drag a scope block to make a copy of it, change its name. And let me go back into the Simulink browser, go into Math, and I'm going to grab this add block. Even though it has two plus signs in it, if I left-click, I can go in and make it into a plus minus. So now I can difference those two signals. And you can imagine what I'm going to stick into it. Well, the first thing I'm going to do actually is drag this input, that nice little pulse train, and bring that in here, because I'd like to see that as a reference. And of course, smooth out the lines a little bit. And now I'll just right-click and drag. That'll give me a little line off of that line. Right-click and drag, get another little line. And now I'm differencing the signals of the state space and the transfer function. And might as well call this errors M, meters. Run it. Take a look at it. So we see the pulse train on there, and we see the difference between the transfer function and state space responses in blue. And so you can see the little transient behavior, and then it's 0 after that. So after the transient dies out, it really doesn't matter if you were looking at a transfer function or a state space. So the moral of this story is, if you're interested in state space, or if you're interested in initial conditions, use a state space. If you're not, a transfer function. But really the important thing here is just a brief introduction to Simulink. So there you go, a very brief and very selected introduction to Simulink. I hope you've enjoyed this as much as I have, and I want to thank you very much for watching. As always, this is Gordon Parker from Michigan Tech, and best of luck to you with your Simulink work.